All right, so let me start off by telling you why we pursue nuclear power, okay? So what I'm going to do is these next 5 minutes are crucial. You want to understand, you want to be awake for these next 5 minutes because the next two chapters depend on this stuff, okay? So you want to understand the next 5 minutes. Well, okay. So here's why we like nuclear power, okay? 1 kilogram of nuclear fuel will give you the same energy as 3 million kgs of coal and 2 million kgs of oil. Okay. So the energy density is a millionfold. Okay. Did you guys understand that? So roughly 3 million pounds of coal has the same energy content as 1 pound of nuclear fuel. Yeah. To put it another way, okay, if you go to the parking lot and pick up any one small car, and if you could turn all of it into energy, you could run the US for an entire year. Yeah. Obviously, that's not easy to do, but okay, if you could do that, you could. Okay. And the energy content of mass, this equation that you all have seen and that Mr. Einstein came up with, okay, that's this is mass, that's the speed of light. And so mass has a lot of energy content, except that if it's hard to convert it all into energy, okay? So that's why we pursue nuclear energy, okay? The US currently has 100 nuclear power plants, okay, producing 100 gigawatts worth of electricity. What is a gigawatt? That's what a Hoover Dam does. So 100 Hoover Dams worth of electricity is produced by nuclear energy, okay? Here we get 20% of our electricity from nuclear power. Okay. In the world, there are 450 nuclear power plants producing 400 gigawatts of electricity, 400 Hoover Dams worth of electricity. Okay. France gets 75% of its electricity from nuclear power. So again, in the world, 450 nuclear power plants. There are about 60 new power plants under construction. You know, 200 have been shut down because they've aged out. In the world, 10% of the electricity comes from nuclear energy, nuclear power plants. Okay. Okay, so I'm just giving you a 30,000 foot view of why nuclear power is good. Okay. A capacity factor. Anybody heard of this thing? Do you know what this might mean? Okay. So what this means is the following. By the way, so roughly, here is a number to keep in mind. What is a gigawatt? Gigawatt is roughly, I'm sorry?
Billion?
Yeah, it's 1 billion watts. That's what a Hoover Dam produces. Okay, and if you have $3 to $5 billion, you can put out a gigawatt worth of solar power or wind power. Okay. All right. So let's say you have $5 billion and you invested in a solar plant or a wind plant. What do you want that $5 billion to do? You want it to be working all the time, right? If you put that kind of money. Okay. A solar plant, now solar and wind are the best. That's where I would put my money. Okay. but half the time the sun is not operating, so your $5 billion is operating 25% of the time. That's what this number says. Okay? The maximum rated power. When is your solar plant generating the highest power?
In the summer.
I'm sorry?
In the summer.
In the summer at noontime. Okay? So if it was as sunny as noontime all the way through, you can imagine the 100% power. So it produces a quarter of that, half of that because it's night and all that kind of stuff. Okay? So that's what that means. Okay? A coal power plant, $5 billion is working half the time. Look at that. A nuclear power plant works 95% of the time. You invest your money, it's working all the time. Yep. All right. So that's a good investment. Now here's another thing about electricity. Okay, so you got to understand this. All right. So let's say this is the hours, time of the day, and amount of electricity produced. Amount of electricity used. So power usage. Okay. So let's say during the day electricity use goes up and down like that. Okay. Now the thing with electricity is, if this is the amount being used, that's exactly how much you got to produce. Okay. So if somebody gets up and shuts off the lights, that amount of production has to go down. I'm kidding you not. So you go shut down the light, and at some power plant, that much less power has to be produced. All right, so it turns out that, for this base amount of power, you have to have this much power all the time, electricity all the time. For this guy, nuclear is the best. Yep. Now, within your lifetime, everything will run on electricity. So for the base load, nuclear will be the best. Yep. Now, in fact, you could have this much nuclear power. Okay. So see, during this times, this is also producing a nuclear power. But what happens if you had this many nuclear power plants? What happens when you're producing too much electricity? You can't shut down a nuclear power plant just like that. But if you were rich and you invest in enough batteries, when you're producing excess power, charge the battery and then use it there. Okay, did you guys understand that? Okay. So right now, batteries are expensive. And that's what's stopping us from going wind and solar and nuclear. Okay? So if you want to become rich, just invent a cheap battery. Okay? Not small battery, enough battery to run cities and stuff like that. Okay? All right, so for base load, this is called base load, nuclear is the best. Okay? All right, did you guys understand all of that? Okay, now we'll understand the physics of nuclear energy. Okay? And I'll keep it very basic. We'll keep it very, very basic because that's all I understand. Okay. All right, let's go shopping. You guys know what atoms are made of? What are they made of? Very good, my friend. I love you. Protons, neutrons, and electrons. What's that? Go ahead.
She said croutons.
All right. Well, croutons do have atoms in them. All right. So now these guys are heavy. These guys are very light. So these guys are about 2,000 times heavier than this guy. Okay, these guys have protons and neutrons roughly weigh the same, and they're 2,000 times heavier than that. Okay, so let's go shopping and we'll buy one proton and one electron. And I'll say the mass of this guy is 2,000 units, this mass of this guy is 1 unit. Okay, and what we'll do is we'll make the hydrogen atom, that guy in the very top left. Okay, so, and you guys, I know you guys are all, okay, so there's the proton. And what are these? These are the atomic levels of the hydrogen atom. And what I'll do is I'll put an electron there. Okay? So what did I do? This actually is an excited state of hydrogen. I took a proton and an electron and made this hydrogen atom. Yeah? In this, we all know addition. Okay. How much does this guy weigh?
2000.
I'm sorry? 2001. Okay, that's what every smart person would say. It weighs less than 2001. Am I pulling your leg? Why does it weigh less? Okay, so, I'm sorry? No, the electron was 1 unit, so 2000 plus 1 is 2001. But it weighs less. Okay, so here's the deal. So this is the secret to nuclear energy. I mean, we're building toward that. Anytime you take ingredients and you form a bound state, it weighs less. Okay? Well, so this thing weighs less. So what happened to the missing mass? That got converted to energy, and in putting this together, that energy was radiated away. It's crucial you understand this. You guys understand? Okay. All right. How about this guy? Hi. We waited for you 3 minutes, but then we couldn't wait any longer.
Oh, you actually waited? Well, I'm so sorry everyone that waited on me. You
Well.
shouldn't have.
We were going to boo when you came in, but we decided not to.
That's
All right.
really awful, so I'm glad I didn't come in 3 minutes late.
All right. So had we made the atom like this, which one would weigh more? This guy or this guy? I'm sorry?
The bottom one, because it's less excited.
So it's more tightly bound and it would weigh less. Did you guys understand that? So the tighter you're bound, the less you weigh. Okay? And that energy is converted. That missing mass is converted to energy. Okay? All right, so that's the secret to nuclear energy. Except that this is atoms. Okay, now what we're going to do is we're going to build nuclei. Okay, so what I'll do is I'll first start off by doing a model for one of the atoms. So let's do carbon. Okay, so carbon 6. So what this notation is this is the symbol for the element, carbon. What does 6 tell you? I'm sorry? Go ahead. It tells you the number of protons it has, okay? And this number tells you the number of protons and neutrons it has, okay? So this is protons plus neutrons, this is protons. And what identifies an element is how many protons it has, and that's how many electrons it has and so on, okay? All right, so let's put together carbon. Okay, so here's the nucleus. And I'll make the neutrons blue and the protons red. 3, 6. And then since an atom is so, and here are the electrons. So this is the carbon atom. Okay. So it has 6 electrons, 6 protons, and 6 neutrons for this carbon. Okay, for this carbon atom. All right. Now let me tell you the size of these guys. Okay. 10 minus 10 meter, and the size of this thing is 10 minus 15 meters. Now these numbers might not mean anything to you guys. I'll scale them down. I'll give you an analogy. Okay. So what we are saying is, what this means is the nucleus is 100,000 times smaller than an atom. Yeah. Have you guys seen an atom? No, they're very tiny. You can't see them. Okay. Atoms are very tiny. Nuclei are 100,000 times tinier than that. Okay, so if this atom were as big as a football stadium, the nucleus would be the size of a marble at the center. Yeah. This is the guy we are going to mess with. Okay. In nuclear reactors. We're going to mess with the nuclei. Okay. Now you see that this is a bound state. When you took a proton and an electron and they form a bound state, they weighed less, right? So if you went to Walmart, bought 6 protons and 6 neutrons and put this nuclei together, the mass of this would be less than the 12 protons and neutron weighs, right? Did you guys understand that? All right. So we've understood all of that. Do you guys have any questions? Okay, go ahead. You're shaking your head.
I don't have any questions, I just don't understand it.
Did you understand this part? When we said you took a proton and, were you here by then?
Mm-hmm.
Okay. You took a proton and an electron, made a hydrogen atom, and this guy weighed less than the mass of the proton and the electron by itself. The thing is, whenever something forms a bound state, it loses mass, and that is emitted as energy. Okay, it weighs less. And the secret is, the tighter it's bound, the less it weighs. Okay?
I don't understand that part, the tighter was bound.
Oh, the tighter, the particles are bound, the proton and the, so here was the other. So here is proton. Now I'm using an atom. So here is the proton and the electron. This is an excited state. And if the electron was here, see, if the electron is in that level, it's not as tightly bound as it's in this level. Okay? Did you understand that? So the tighter it's bound, the less it weighs. Okay? All right, now we have graduated to building nuclear reactors. Okay.
Thinking it takes more energy to take one of
Take them apart. Very good, my friend. What's your name? Huh?
Logan.
Logan. Okay, so if you wanted to bust this guy over, it takes more energy to bust this over than bust this up than this guy. Right? Okay. All right. We ready to build nuclear reactors? All right. So see, she came 3 minutes late and she's ready. All right. You'll hear that till the end of this period. All right. Now, so what is useful in talking about this stuff is, okay, so now we'll change our tune. We'll put numbers just so we understand stuff. Okay. We'll say a proton weighs 100 units. Yeah, just a proton and a neutron weighs 100 units. When we build nuclear reactors, what we'll use is uranium-235. Okay. Okay, so let's see if you guys remember. What does this number mean? I'm sorry? Number of protons. Very good. And what does this number mean?
Protons and neutrons.
Yeah, that's right. Protons and neutrons, right? All right, and as far as nuclear physics goes, we'll treat them the same. So one color is proton and the other color is neutrons, okay? So this is protons. Well, anyway, we won't worry about that. All right, so this is uranium-235. What we are going to do is we're going to split this into two pieces, two nuclei. In this guy, I'm just making up numbers, okay, just for so you guys understand this. In this guy, each proton and neutron weighs 95 units. You split them up. In these pieces, each proton and neutron weighs 92 units. Yeah. Let me change that number, 93 units. What happened?
By splitting it as a unit?
I'm sorry?
When you split it, it adds a unit?
Say that
From
again.
92 to 93, you said, right?
Oh, no. Oh, forget I wrote 92. Okay, so this was a bound state. That's why each one of them was weighing less than a free neutron and proton. You guys understand that? And then I took this large nuclei. I haven't told you how I'm going to split it, but we'll come to that. We have 3 hours to do that. I'm going to split that and roughly equal pieces. And in each of these pieces, now the proton and neutron is weighing less.
Because they're more closely.
Very good. Very good. They're more tightly bound. So these two pieces together weigh less than this piece. What happened to the missing mass?
And it's radiated energy.
That's right, it got converted to energy. Mr. Einstein tells us the missing mass got converted to energy. And that's a lot of energy. You just saw that earlier. 1 kg of nuclear fuel contains the same amount of energy as 3 million kgs of burning coal. Okay? Well, so when you split this, all that energy shows up as heat. What I didn't tell you was, okay, so now let me fill in the details. Did you guys understand all of that? Okay, so now and again, like I said, we have 2 class periods to talk about this. Okay, how do you split this nucleus? You go buy a neutron gun, shoot, sit down.
Fission?
Yeah, that's the fission reaction. Okay, so very good. So you buy a neutron gun, shoot it at the nuclei, and then eventually it'll split. And thankfully, it spits out 3 more neutrons, and you can use this to split another nuclei and so on, and then keep a chain reaction going. Okay? And all that energy showed up as heat. Heat in these guys. Okay, so those guys are all hot. What do you do with heat? I'm sorry? You boil water. You boil water, you make steam. What does the steam do? Steam, it does evaporate. It turns a turbine. And what does the turbine do? That's
Do you
what the
know
job
how
of the
an
turbine is.
electric generator works? Electric generator converts mechanical energy to electrical energy.
So you guys are all experts. That's how a nuclear reactor works. Did you guys understand that? Yeah. All right. So again, let's make sure we understand this. So in a nuclear reactor, you take a heavy nuclei, split it into 2 pieces using neutrons. These 2 pieces when you split it into 2 pieces, normally what you get is two equal pieces, roughly equal pieces, and three neutrons. These guys weigh less than the products weigh less than the ingredients. Why do these guys weigh less? Because they're more tightly bound. Okay? And that energy is used to produce electricity. Same thing happens when you burn wood. When you burn wood, what are the ingredients? Wood and oxygen. What are the products? Ash, carbon dioxide, and water vapor. And the products weigh less, and you get energy. Except that in that case, you get 1,000,000 times less energy, so you're not interested. You guys are all very sophisticated, and you're all ready to build nuclear reactors today. Okay? All right, do we understand that? Okay, so now we have to go through some of the details. Okay? And so you just have to patiently listen to all of that. Okay, so let's get on with it. And I trust you guys, I will just point out the highlights on the slides, okay? All right, so so again, here is the electron cloud surrounding a nucleus. Again, what is the size of an atom? The size of an atom is 10 to the minus 10 meters. The size of the nucleus is 10 minus 15 meters. So if this was as big as a football stadium, this would be as big as a marble. Okay, and that's what we're messing with in a nuclear reactor. Okay. So electrons have negligible mass. Each proton weighs how many times that of an electron? 2,000 times that of an electron. Okay, so a nuclide is a nucleus, a specific number of neutrons, and a number of protons. Number of protons is denoted by Z. Number of neutrons is denoted by N. Okay, okay, so in this case, in this atom, the blue are the neutrons, and the red are the protons, and it has 3 electrons. Okay, so 3 protons and 3 electrons. Okay. So again, A is the mass number, Z is the atomic number, which is the number of protons, and this is the symbol for the element. Okay. You sort of want to know an atomic mass unit. Okay. So whenever you want to talk about the mass of a single atom and stuff like that, this is a good unit. Okay. An atomic mass unit. So and this is defined as follows. The mass of carbon-12 is defined as exactly 12 atomic mass units. Okay? So that's how we define it. All right, so those red numbers on the periodic table, okay, those are the masses of those atoms in atomic mass units. So in the periodic table for the lithium, let's see, lithium, it says 6.941 atomic mass units. Okay. Now we'll talk about something called isotopes. And in nature, there's various isotopes of lithium. So that's the average mass of a lithium atom. Okay, weighted for all those isotopes. Okay, so that's what that is. The word nucleons means protons and neutrons. Okay, inside a nucleus, we treat the proton and the neutron the same. Why does this keep happening? All right. So what are isotopes? So here are isotopes of oxygen, oxygen 16, 17, and 18. Okay. What makes an oxygen? It's the number of protons that makes an oxygen. And if you look at the periodic table, for the oxygen, that number 8 tells you that it has 8 protons. Okay? So that's what makes an oxygen. So it has 8 protons. Oxygen 16, this is the number of protons and neutrons, so it has 8 plus 8, 8 protons and 8 neutrons. This thing, oxygen 17, 8 plus 9, okay, 8 protons and 9 neutrons, 8 plus 10, 8 protons and 10 neutrons. Okay, these guys are just heavier. Yeah. So how many electrons does the oxygen have? All oxygen, they all have 8 electrons. Yep. And all chemical properties, so for oxygen, there's the inner shell, there's the outer shell. Okay, so all chemical properties of oxygen are determined by these outermost shell. They're called the valence electrons. Okay, so these isotopes are heavier, but their chemical properties are identical. So you can't separate them chemically. Okay, what does oxygen want to do in its life? Okay, in all chemical reactions, what you want to do is you want to either complete a valence shell or empty it. Okay, a complete valence shell is 8 electrons. So everything oxygen does in its life is to acquire 2 electrons. Okay, how can it do that? You guys understanding this? We're going a little all over the place, but so here's one way of doing it. What is this? Hydrogen. So it talks, an oxygen molecule, atom will talk 2 hydrogen atoms to share their electrons, thereby getting a full valence shell. Okay, and what is this guy?
Water.
It's the Mickey Mouse molecule, right? All right, so what are isotopes? Isotopes are elements which have a different number of neutrons, so they're just heavier, but they have identical chemical properties. Okay, so just remember that. All right, so here are isotopes of carbon. Carbon 12, that means carbon has 6 protons. All carbon atoms have 6 protons. This is carbon 12, so 6 neutrons, 7 neutrons, 8 neutrons. Okay? And what this tells you is, so here's the mass number, here's the number of neutrons, and here's the mass number. And this is all carbon. And you see carbon 14 that has 8 neutrons is unstable, and it has a half-life of 6,000 years. We'll come to that later. Okay, we'll talk about that. You guys know carbon dating? Anybody heard of carbon dating? Yes, no? Who hasn't heard of carbon dating? Let's see a show of hands. So you guys have read things like, okay, archaeologists will find, okay, and say that, hey, this spot is 20,000 years old. How do they know that? I'm sorry?
They dig in the ice or deep down.
No. Let's say they'll find a coal deposit, and the coal deposit is, okay, well, not a coal deposit, it can't be used for that. But let's say there's a woolly mammoth that they found. That's 20,000 years old. So we'll learn how to do that, okay? So remember this number. I'm sorry?
I was remembering that number.
Okay, yes, that's 6,000 years, okay? All right. So nuclear stability, what this means is, so let's say we put together a nucleus like this. We went to the store, bought a bunch of protons and neutrons, and put this nucleus together. Okay. Now, what this graph is telling you is, see, this is the number of neutrons you put in. This is the number of protons. Okay. So if you take 60 protons and you had only 40 neutrons, you couldn't make a stable nucleus. If you put together a nucleus, that would decay. Okay? You guys understanding this? And we'll see how an unstable nucleus decays. Okay? So the only stable nuclei you can put together is in the dark blue area. So if you're putting together a small nucleus, the number of protons and neutrons have to be equal, roughly. Okay? If you put together a nucleus in this light blue area, it'll be unstable, and it will radioactively decay. And where will it go? Where will the light blue nuclei go?
Atmosphere?
I'm sorry?
The atmosphere?
They will move toward the dark blue area. Dark blue is stable. Did you guys understand that? Okay. Yes? No? Okay. So what we're doing is we're putting together nuclei, and if this nuclei is unstable, it will radioactively decay, and we'll learn how it'll decay and move towards stability.
So it'll lose.
Oh, so
neutrons?
I'm sorry?
Will it like lose neutrons?
Yeah, so all right, so let's talk about it. So here's an unstable nucleus. Okay, so it can become stable by doing one of three things. It can alpha particle, it can emit an alpha particle, a beta plus or minus particle, or a gamma ray. Okay? An alpha particle is a helium nucleus. It's 2 protons and 2 neutrons. A beta plus or minus particle is, and this is a electron, this is a positron or an electron. Okay, when this happens, either a neutron gets converted to a proton plus electron plus something called a neutrino, or inside the nucleus a proton gets converted to a neutron plus a positron plus so this is an anti-neutrino and a neutrino. Okay. So here's what we're talking about is here's a nucleus that is unstable. What does unstable mean? It's in that light blue area. And of course, it doesn't want to be unstable. It wants to become a stable nucleus. Okay. And so what it does is it radioactively decays. Okay. Depending on its state, it will either emit an alpha particle. An alpha particle is just a helium nucleus. So it loses 2 protons and 2 neutrons. Or one of the neutrons or protons can get converted to, a proton can get converted to neutrons, or a neutron can get converted to a proton, if that's what it wishes for stability. Or this could just be in an excited state and emit a gamma particle. Okay? So a beta decay, again, I know this is complicated. In a beta decay, either a neutron is getting converted to a proton or a proton is getting converted to a neutron. Yep?
Does that mean unless it's putting gamma rays, it's always going to convert into a different type of atom? Or
That's right.
Okay.
This is the only way. So what were those guys? Alchemists seeking gold, trying to convert different materials into gold. Yeah. So radioactive decay is the only way you can convert elements. Okay. All right. We'll come to that. Okay. So all I want you to remember is if you go and buy a whole bunch of protons and neutrons and put together a nuclei, you'd better be here if you want to construct a stable nucleus. Okay. Notice something. See, this line is where neutrons is equal to protons. So as you put larger and larger nuclei together, you have to have more neutrons. Why might that be?
So it's more stable?
Yeah, it's more stable. Okay, so um, so protons are positively charged. What do and neutrons have neutral charges. What do protons want to do? They don't like each other. They want to repel each other. So if you have a nucleus with a whole bunch of protons, to keep them further apart, you put together more neutrons. Yeah. So the larger the nucleus, the more neutrons you want. Okay. All right. Is it getting deep? I mean, I see that I'm losing some of you guys. You guys, yes? All right. All right, so this tells you a little bit about nuclear stability, but all I care for you to remember is if you want to build a stable nucleus, you have to be in the dark blue area, and that'll tell you. So this tells you, so for instance, if you had this nucleus that has 80 neutrons and about 55 protons, okay? That's a stable nucleus. And if you're in the light blue area, that'll be unstable, and those guys will move towards stability by radioactive decay. Okay? And if you're not in one of those areas, you don't exist. Okay, you can't build those nuclei. So you couldn't build a 80 proton and a 40. So you couldn't build this nucleus. That's 80 protons and 40 neutrons. You couldn't build that guy. Okay. So that's what that graph tells you. So this is a very expensive graph, but you already understand this. Okay. So now let me do an example. Okay, so here's the experiment we'll do. We'll take 4 protons and we'll make it into a helium nucleus. Okay. What do you notice here? What's happening here? This is a bound state. Okay. So let's say each of these guys weighs 100 units. So that's 400 units. How much does this guy weigh? I'm sorry?
How much did you say it weighed?
So each of these guys weighs 400 units, 100 units. How much does this guy weigh? This is a bound state.
Less than 400.
Less than 400, very good. Okay. And now in this thing, what I didn't tell you is, in the process, we converted 2 protons into 2 neutrons, but that's minor details for now. Okay. This is what our sun does. This, very good, my friend. Very good. So it's taking 4 neutrons, 4 hydrogen nuclei, and converting it into a helium nucleus, and that's how it gets. It produces energy, plus energy. Okay. Okay. How much mass does it lose? It loses about 1 part in a little less than 1%. Okay. So that's how much mass it loses. So over the lifetime of the sun, which is 10 billion years, it'll lose 1% of its mass. Okay, so this is a fusion reaction. That's how the sun produces energy. Okay, so now I'll just make up some numbers. Now let's say each of these guys weighs 95 units inside the helium nucleus. Okay, so 5 units, each of the nucleon weighs 5 units less. And that's what this graph is showing you. So mass per nucleon. Okay. So this is the mass of the nucleon when it's free. This is the effective mass of the nucleon in these various atoms. So this is what it is in helium. This is what it is in whatever element. And in iron, that's the most tightly bound. Okay, so stars fuse atoms till they get to iron. They can get energy till they get to iron. Okay, so this is fusion reaction. Did you guys understand that? So what you want to do is you want to put together stuff where the protons and neutrons are weighing less and less. Okay, so you can take light nuclei and fuse them, so and get their fusion reaction, or you can take a heavy nucleus, and if you split it into two smaller pieces, see these guys weigh less, so you'll get energy. Okay, did you guys understand that? Fission, which is what we do on Earth. Okay, what is this saying? See, in uranium-235, that's the mass of each proton and neutrons, and you split it into these two pieces, each proton and neutron weighs less, and so you're getting energy. Okay? So this is easier to do, and that's why we're doing this. Okay? Now, what we'd like to do is this. The reason we would like to copy the sun is because this guy is not radioactive. These guys are radioactive for 25, 30,000 years. Okay? And it's a minor problem compared to global warming. Okay? So speaking of which, so here's the third advantage of nuclear energy. Okay, so which I forgot to mention. So 1 kg of nuclear fuel gives you the same amount of energy as 3 million kgs of coal. And what is the other advantage? This is the biggest advantage, no CO2. Okay, it has no carbon footprint. So nuclear energy is great because of that. Okay. All right. I'm going to have to. All right, let's make sure we understand this graph. So in a bound state, a proton and neutron will weigh less, and so this tells you how strongly the nuclei are bound. Okay, so this is the effective mass. So in this element, that's how much a proton and a neutron weigh. In this element, that's how much a neutron and proton weigh. In this element, that's how much a neutron and a proton weigh. And this is the mass of the free neutron and proton. Okay? All right, so here's that graph inverted. Okay. So this is the binding energy per particle. So if you took a free proton and put it in iron, this is how much energy you would get out. Okay, so that's what that graph tells you. Okay, so essentially, it's hard to read these numbers, but essentially, okay, so if you take four protons, what this graph is telling you, and put it together in a helium nucleus, okay, what it's telling you is, so this is roughly 7 MeV per nucleon, per particle. So you would get 7 times 4, 28 MeV of energy when you put this bind, okay?
What does MEV stand for again?
Million electron volts, okay? All right, so again, you guys understand, take lighter nuclei and fuse them together. They're more strongly bound and you get energy, or you can take a heavy nucleus and split it into 2 nuclei. They're more tightly bound and you get energy. Okay, and this is what we do in nuclear reactors. Okay. So nuclear energy can be obtained by fusion or fission. Fusion is the process of combining smaller nuclei to form larger nuclei up to iron. Fission is the process of splitting large nuclei like uranium into smaller ones to get energy. Okay. So this is what we've been doing for about almost 80 years. fusion we've been trying to do for the last 50 years. Okay? And we are getting close. All right. So this chart explains one of the mysteries. Okay, so nuclear energy. How much more energy do you get per kg, per pound? So 1 pound of nuclear energy gives you the same energy as 3 million pounds of coal. So nuclear energy is 3 million fold larger, pound for pound. Okay. All right, so why is that? Okay, so let's go back to our. Okay, so this is a nucleus we built. Okay. And these guys are protons. Right, what do the protons want to do? They repel each other, right? So your body is full of atoms which have nuclei, and if these protons flew apart, then the nucleus would be unstable and you wouldn't be alive. How come nothing is happening to you? How come these protons are not flying apart? I'm sorry? So what? I mean, they'll get out of the way. You guys understand the question?
Do we add more neutrons to make it an isotope and then
These guys don't care what is around them. They're repelling each other.
Oh, the electrons.
No. The electrons would make the problem worse. Here's an electron. He's egging him on. He's attracting him too.
Oh, yeah.
Yep.
The opposite force of atoms around it?
No. So you guys understand the question now. So if they're not flying apart, that must mean that there's a stronger force that's attracting them. And that is the strong force. And that strong force is 100 times stronger. So the electromagnetic repulsive force is 100 times weaker. Okay, so this repulsive force is 100 times weaker than the attractive force. Okay, and the strong attractive force is what's keeping them together. And because the strong force is so strong, that's why the bound state loses so much mass, and that's why you get so much energy out of nuclear energy. Okay? Now here's go ahead.
What is the strong force?
Well, so in nature there are 4 forces, and this is one of them. It's mediated by gluons and stuff like that. So this strong force, it has a range of only 10 to the minus 15 meters. What that means is, for these two guys to feel that strong force, they have to be within 10 to the minus 15 meters. And that's why all the nuclei are that small.
what are the hadrons that was on that chart?
Yep, the hadrons are neutrons and protons. They feel the hard force. And there are other particles. Okay. So this tells you what charges feel what things feel the strong force. Okay, so the strong force is 100 times stronger than the electromagnetic force. Okay, and when you do chemistry, you only mess with the electromagnetic force. So the energies involved when you burn stuff, the energies involved are much smaller. Okay, so that's why burning coal, you get 1,000,000 times less energy. It's because of the strong force you get a large amount of energy. Okay. So here's Einstein's relations. And again, if all the mass of a small car could be converted to electricity, one could satisfy the energy needs of the US for a year. You could run the entire planet, the entire world on 4 small cars a year. Okay? So every year we just go to the parking lot, pick out 4 cars. All right. This shows you the binding energy calculation. You don't have to worry about it. What this is telling you is how many, this is the mass of free neutrons, this is the mass of the free protons, and this is the mass of the bound nucleus. Okay, so this obviously weighs less than these guys, and that's how much energy is released when you put this nucleus together. Okay, so if you wanted to pull this nucleus apart into protons and neutrons, you would have to put that much energy. Okay, the more strongly it's bound, the less mass it has. Which is the only nucleus out of which you cannot get energy? Very good, my friend. Okay. Iron is the most strongly bound nucleus. Okay. That's what we saw. Okay, iron is the most strongly bound nucleus. Okay, so you can start with a smaller nucleus and get to iron. You can get energy. So all stars, massive stars, will get energy until they get iron. And to produce all these heavier elements in the stars, you need energy. And that's where supernova explosion happens. Okay, that's when all those guys are produced. So up to iron you can get energy, and you can get energy up to iron from this side. All right, I'm just going to quickly point this out because I got to tell you a couple of stories that are important. So what this is showing you, is this table is showing you, is you're going to put together a nucleus of 49 protons and neutrons. Okay, you're going to keep that constant. What you're going to change is the number of protons. See, this is 29 neutrons, 20 protons, that's 49, 28, 21, 27, 22. And what you'll see is roughly so you always have to have greater number of neutrons. Okay, but if you had too many neutrons, it would be unstable. This guy is stable. Okay, this doesn't have enough protons in neutrons, and that's unstable. Okay, so half-life is 330 days, and this is unstable and it'll decay. This is unstable and it'll decay. Okay, only this guy is stable. Okay, so you have to have the right mix of neutrons and protons, and we'll talk about half-life in a second. Okay, so that's what that is showing you. All right, so I want you to make sure we understand this term, beta decay. In a beta decay, inside the nucleus, a neutron will get converted to a proton plus an electron plus an antineutrino. Or a proton will get converted to a neutron, a positron plus a neutrino. Okay, see, the neutron had zero charge, a proton has positive charge, so you have to spit out an electron. This negative charge cancels a positive charge and an antineutrino. This kind of stuff in the sun, a proton is getting converted to a neutron, remember when it becomes a helium, plus a positron plus plus a neutrino. And right now, so the sun is producing trillions of those, and right now trillions of those are going through your body right now. Hold up a finger like that, and trillions of those every second are going through these guys. They interact very weakly, and so they're not messing with you. Okay? All right, so when a beta decay happens, a neutron is being converted to a proton, or a proton is being converted to a neutron. Okay? All right, when a nucleus, you built a nucleus, and if it's unstable, what happens? It undergoes radioactive decay to become a stable nucleus. Okay, so if you're unstable, you do whatever to become stable. And there's one of three ways you can have radioactive decay. you can spit out an alpha particle. An alpha particle is a helium nucleus, or spit out a beta particle. A beta particle is either an electron or a positron. Okay, you guys have heard of antiparticles. Positron is an antiparticle for an electron. Okay? So this is the beta decay. So these nuclei are unstable, and they're trying to become stable by emitting an alpha particle or a beta particle or a gamma ray. Okay, this is just an excited nucleus, and it gets de-excited. Okay, so you have radioactive decay because an unstable nuclei is trying to become a stable nucleus. Okay. Yep.
What is the difference between an alpha, a beta, and then the gamma?
An alpha particle is a helium nucleus, so this is very heavy nuclei that'll emit an alpha particle. In a beta part decay, so let's say, so we'll use carbon-14. Okay, carbon-14 has how many? 8 neutrons and 6 protons, right? So carbon-12, so you will be able to answer this. Well, carbon-12 has 6 protons and 6 neutrons. This guy is stable. Carbon-14 has 8 neutrons. That's unstable. Okay. How would you make it stable? How can you make it stable? I'm sorry?
Moving back 2 extra neutrons.
If you could convert a neutron to a proton, you can make it stable. Right? And that's what happens. That's the beta decay. A neutron gets converted to a proton inside the nucleus. And so carbon-14, a neutron gets converted to a proton, and so it'll have 7 neutrons and 7 protons, and this is nitrogen. So carbon-14 will radioactively decay and become a nitrogen atom. Okay. You guys understand this?
What is the gamma doing?
Oh, the gamma. Okay, so let's make sure. These are 3 different modes. It's not the same nucleus that's decaying. This is a heavy nucleus that decayed like this. This is another nucleus that decayed by beta decay. And this is another third nucleus that decayed via gamma ray. Okay. We'll come to that in a. We'll come to that. Okay, because there's stuff I want to tell you guys. Now let's do the following. Let's say you were rich and you bought 1,000 of these unstable nuclei. Okay. What are the nuclei going to do? They're going to try to become stable. How are they going to become stable? Radioactive decay. All right. So if you watch this guy, you don't know if he's going to radioactively decay. They can randomly radioactively decay. You don't know which one is going to decay. So it's a random process. The half-life tells you after this time how many of them will have decayed. That's all you can say. Okay? So if you started off with 1,000, and if the half-life is 500 years, after 500 years, I will make this different. I'll make it 200 years. Half-life is 200 years. After 200 years, how many do you have left?
500.
Very good. After 400 years, how many do you have left? 250. Okay. Out of 600 years?
125.
125. That's what half-life means. All right, so now you're ready. Now now you're ready to understand this. Okay, so I'm a carbon-based life. All organic matter is carbon-based life. Okay, so in my body, okay, so this is a constant ratio. Every billionth atom is a carbon-14 atom. Okay, and for every billion carbon-12 atoms, I have one carbon-14 atoms. Okay, it's very easy to estimate how many total carbon atoms I have in my body, and then a billionth of that is that. Okay, so let's say I have 10,000 carbon-14 atoms in my body. Okay, right after this lecture, I die. Yep. And then you come back. So let's say I died right after this lecture. After 6,000 years, 6,000 years is the half-life. How many carbon-14 atoms will be in my body? 5,000. After 12,000 years, 2,500. That's how you carbon date. Okay, so some organic matter died. You know how many carbon-14 atoms it initially had. Okay, and then you measure how many there are right now. Okay, so that's how many years ago it died. That's carbon dating. Did you guys understand that? Okay. What if you had to date something that was 4 million years old? So you can't use this. So you need a clock that has a longer half-life. Did you guys understand that? Okay. So you just use different clocks. How do we know that the Earth is 4.5 billion years old? You have to use an appropriate clock. Uranium. So uranium-238 has a half-life of 4.5 billion years. That's a good clock. That's how we know that the Earth is that old. Okay. So, but before I come to that story, let's make sure we understand this. Okay. So you have a bunch of unstable nuclei. They will randomly decay. The half-life tells you after that period, half of them have decayed. Okay, that's what that tells you. Okay, you don't know when any specific nuclei will decay. Okay, you can only make statistical information. Okay, so the number decreases exponentially. Okay, so n naught is the number you started off with, and then the numbers will decay exponentially.
So if they're stable, they don't decay.
I'm sorry?
If they're stable.
That's right. If it's stable, if you're rich and happy, there's nothing you need to do, you know? Okay, so only unstable nuclei decay. And which were the unstable nuclei? Which were the unstable nuclei? I'm sorry? The one in the light blue areas. Okay? Let's go to the Sergey plot. Where is the Sergey plot? My friend. Oh, there. The light blue areas are the unstable ones, and they're trying to get to the stability area. Okay? All right. So large unstable nucleus, smaller, more stable nucleus. So an alpha decay happens when a large nucleus will spit out see, this is taking a big step. So it's spitting out a helium nucleus, okay, and it's trying to get to stability, okay? That's an alpha particle. So here's an example. So here's uranium-238. See, it has too many neutrons. The neutron to proton ratio is too high. It'll spit out a helium nucleus, and it becomes thorium. Okay, so this is a daughter nucleus. So this is the alpha decay, and the half-life is 4.5 billion years. I mean, this just doesn't happen like that. So if you have 100 uranium-238 nuclei, you got to wait 5 billion years before you have 15 uranium-238 nucleus. And you don't know which ones are going to decay. Okay, it's a random process. Okay, it's like a coin toss there. In a beta decay, either a neutron is being converted to a proton or a proton is being converted to a neutron, depending on what is your situation. If you have too many neutrons in your nucleus, you convert one of them into a proton. If you have too many protons, you convert one of them into a neutron. Okay? Whatever gives you stability. Okay? That's what's happening. So here's carbon-14. In this carbon-14, what did you have? Too many neutrons. So what did you do? You converted one of the neutrons to a proton, and then you became a nitrogen. Okay? And this happens with a half-life of 6,000 years, 5,730 years. Okay? And that's what's, this decay is what's used for carbon dating. Okay? A gamma rays, okay, so generally what happens, the daughter nucleus that's formed, this guy is in an excited state. And that will come, the element won't change. It will decay via gamma decay. So the nucleus will remain the same. It's just a de-excited state. Okay, so the gamma decay happens then. These guys show you what happens. So here's this is radium decaying via alpha particles to radon, okay, and so on. So this is showing you various processes. On a Sergei plot, this is showing you, see, this americium decayed to neptunium via alpha decay. It decreased in neutron number by 2 and proton number by 2. So here's various plots showing you what kind of decay that happens. So this is called a Sergei plot, but we won't worry about that. Okay. So here are nuclear reactions. These guys, so we will, for us it will be important. Here's uranium-235. We'll shoot neutrons to it, and you'll get products out of it. Okay, so here's a nuclear reaction. You're shooting neutrons at this guy. So neutrons and this guy combine, and here are the products. Okay, in nature, carbon-14 is made by neutrons coming from the cosmic radiation. There's nitrogen in our atmosphere. The neutron will knock off a proton, and this will become carbon-14. And that carbon-14 decays into nitrogen-14. So the amount that's produced is the amount that is being decaying. Okay? So the carbon-14 concentration is constant. Okay? And that's, so if, when you're living, every time I eat food, for every billion carbon-12 I eat 1 carbon-14. So I maintain a constant ratio. Okay, that's how we know. And once living matter dies, then the carbon-14 starts decaying. And then you can measure. Okay. Now, I'll tell you this one story and then we'll go. So this is a beautiful story. How the Earth is, how do you find that the Earth is 4.5 billion years old? Okay. So here's a rock called a zircon rock. Okay, so a crystalline rock. And when this is formed, okay, this rock can only incorporate uranium and thorium atoms. It cannot, there can be no lead in there. So when this rock forms, only uranium forms. And then uranium decays with a half-life of 4.5 billion years. The uranium in several steps eventually gets to be lead. Okay? So uranium decays into something, and then that something decays. So there's a uranium decays to lead via a series of alpha and beta decays. Uranium-238 with daughter nuclides undergo a total of 8 alpha and 6 beta processes. But the slowest process is the first process, 4.5 billion years. Anyway, this uranium eventually turns into lead, the blue or the lead. Okay, so here's this rock. You found this rock, and you found this much lead and that much uranium in it. Okay. And here's this graph. They've done a calculate. So if you find this much lead to that much uranium, that rock is 3 billion years old. Okay. So if there's 60% lead and 40% uranium, okay, for every 4 uranium atoms, if there's 6 lead atoms, that rock is 3 billion years old. And uranium-235 and lead-207. So if for about 16 lead-207 atoms and for every uranium-235 atoms, that rock is 3 billion years old. Okay, so that's how they find the age of the rock. All right, guys, there's a couple more slides, but you guys can read that stuff. No quiz today, obviously. All right.